Beyond polynomial space, we can go even higher. Above polynomial space is the set of all the problems that we can solve in exponential time, with maybe exponential memory. Above that is non-deterministic exponential time, where we get to guess something and we're given exponential time to check our guess. So next time is to exp time as np is to p. Above that there's exponential space, then exponentials of exponentials time, and then that amount of space, and so on and so forth, climbing up this infinite ladder of problems which require more and more astronomical amounts of time or memory. Above all of these levels, an infinite number of these levels, is the set of all problems which are computable or decidable. We'll talk about this more when we discuss the Turing machine and the notion of universal computation. But indeed, there are problems which are outside even this class, such as the classic halting problem, telling whether a Turing machine or a computer program will ever halt. As we'll see, that's not something which can be solved in any finite amount of time. So really what all this theory does for us is give us a language to draw qualitative distinctions between different problems, to locate them on this spectrum, in this hierarchy, showing that one problem is qualitatively easier or qualitatively harder than another. And I'm especially fond of this quote by Scott Aronson, who is very much a theoretical computer scientist, that the purpose of computers in all this is much like what we use clocks and trains for when we discuss relativity. As we said at the very outset, computer science is not the study of computers, it's the study of computation. Each of these complexity classes, P, NP, P-space, and so on, represents a certain level of what can be achieved by a certain type or amount of computation, and what problems can be solved within that amount of resources that scales in a particular way with the size of the example. And it's very nice to know that Eulerian paths live at P, Hamiltonian ones at NP. Playing board games is in P-space. The halting problem is all the way up there above the computable problems, and so on. It lets us gain a kind of good intuition about what type of search or what type of proof different problems require. So I said before that the computer science point of view about complex systems asks not so much is a system simple or complex, but what do you want to know? What question are you asking about it? So I want to illustrate this and connect it to our complexity hierarchy that we just saw by looking at a very classic flavor of complex systems, cellular automata. We'll talk more about this in another unit when we go into the basics, the basic building blocks of universal computation. But what you're looking at right now is a space-time diagram of the cellular automaton called Rule 110 by Stephen Wolfram. Time is going downward, and each row of this diagram is a state, a snapshot of the cellular automaton. And you can see that there are some structures that are stationary and oscillating. There are some things that are moving, like elementary particles. There are collisions between these particles that interact and produce new particles as their products. And indeed, it was shown by Matt Cook, confirming this conjecture of Wolfram, and improved by Turlock Neary and Damian Woods, that this cellular automaton is capable of performing universal computation. It can simulate, as we'll see, Turing machines, and for that matter, any other form of computer that you care to name, including the ones in your pocket. Well, if it's capable of doing computation, then asking questions about it will probably lead to hard questions. In particular, trying to predict it means trying to predict an arbitrary computation. Well, that's got to be hard, right? So let's look at a couple of different questions we can ask about this cellular automaton. One is kind of the vanilla prediction question. If I tell you the initial state, and I have a certain number of time steps, t, and I ask you what will the state be t time steps in the future? That's a perfectly reasonable question. I could ask an interesting time-reversed question. I could say, given a state, does it have a predecessor? Is there a state which would lead to this one after one step? That's asking, can the evolution be reversed? Another question. Suppose that I'm doing this on a lattice of size n, maybe with cyclic boundary conditions so it wraps around, and I show you some initial state. Then we're going to run forward in time. I want to know, is this state ever going to return to itself? Is it going to recur? In dynamical systems terms, we would ask, is this state on a periodic orbit? That's another question I could ask. Finally, on an infinite lattice, I could take some initial configuration and I could ask you, will it ever die out? If I keep running this, will there ever be any ones left in the universe, or will it all turn into zeros? These four questions correspond to four different levels of the complexity hierarchy that we just discussed. Your next quiz is figuring out, a priori, what is the complexity class that each of these questions lives in.